I just have a brief announcement. So they tell me students who have posters, they can start, or anyone who has posters, they can start putting them up in the Amoshkali, where we have the parallel sessions, and also the coffee break after this session will be there. So after this, we go to the Amoshkali. So we have our first speaker of the session is Leah Broussard from the Oak Ridge National Laboratory. So she's going to be talking about neutron oscillations. So.
Okay, thank you. Let's see, I need to be on the left side, so thank you very much. Okay, great. Oh, well, I'm very happy to be here. My name is Leah Broussard, and I've spent my career primarily focused on studying the neutron. And today I want to talk about a topic that I think will be very interesting in the future that I'm particularly excited about. And that's searching for baryon number violation using neutron, not neutrino, neutron oscillations. So we have really quite strong evidence that we don't know what makes up the majority of the matter in the universe. Based on our observations of rotational speeds of stars in galaxies, from strong lensing effects and observing the dynamics of colliding galaxies, we're really quite confident that about 85% of matter is what we call dark matter. And this is one of our big puzzles in science today. We also have quite strong evidence that there's virtually no antimatter in the universe. So if you can look at our calculations from Big Bang nucleosynthesis and the cosmic microwave background, we get reasonably, actually very good agreement with our measurements on the amount of excess matter that was left over when the universe cooled. But there's virtually no signs of antimatter. And so that's an interesting puzzle, because you probably would expect equal amounts of matter and antimatter to be created at the Big Bang. So we can't yet build galactic scale experiments or go back in time to try to understand the source of these problems. But what we can do is use a very powerful tool of tests of symmetries. We can perform measurements with rare processes or very precise measurements of standard model observables, and we can follow clues that can help us understand how to approach these questions, and possibly how even to link them together. So the symmetry I want to focus on today is that of baryon number conservation, and similarly lepton number conservation. So just a quick reminder, I'm sure we all remember this, but baryon number is basically just a counting of how many quarks. Ordinary quarks carry a 1/3 charge, anti-quarks carry the negative 1/3 charge. You can build up baryons out of 3 quarks, mesons, those carry baryon number 1. Mesons are quark anti-quark pairs. They don't carry a baryon number. And as far as we've seen in our standard model processes, baryon number is always conserved. And similarly with lepton number, the number of electron-like particles and neutrinos, and conversely their antiparticles carrying the opposite charge, we've never seen evidence of a violation of these numbers. So this is interesting because we follow the guidance from Sakharov, who also very strongly believes in the value of symmetries. If we want to understand the matter-antimatter asymmetry in the universe, the best place to start is use tests of symmetries. And one of the important ones is we must have some kind of process that does not conserve baryon number, and editor's note, or lepton number, in order to create this excess of matter in the universe. So in fact, baryon number and lepton number are actually just accidental symmetries. There's nothing in the standard model that forbids baryon number violation, so we might actually expect to see it. The good quantum number really is B minus L. And in fact, B minus L is conserved in the standard model. But really, to understand baryogenesis, we need processes that actually violate B minus L. So if we approach this there are lots of theories, very broadly speaking, that try to explain baryogenesis. And very broadly speaking, they contain baryon number violation. But the experimentalist approach, I like to think about how to approach this in terms of selection rules. And so we can look at processes which violate both baryon and lepton number violation, but B minus L is conserved. There are processes which only violate lepton number violation. And then finally, there are processes which only violate baryon number violation, or only violate baryon number. So this is a very important problem. We've already expended tremendous experimental effort on answering these questions following these selection rules. So you're probably familiar with searches for proton decay. These originally motivated these huge massive detectors, which eventually we realized were really interesting for discovering things like neutrino oscillations and more properties of neutrinos. But we've been searching for proton decay for a long time. And while we're still planning to build bigger and bigger detectors, we're getting into a place of diminishing returns, where right now the proton decay half-life is greater than 10 to the 34 years. And since the universe is only 10 to the 10 years old, we have to wait a very long time to see a proton decay. Meanwhile, there's also searches for primarily lepton number violation. And here, I think one of the most interesting avenues to pursue, and the one that we're pursuing extremely vigorously, especially in the US, is neutrinoless double beta decay. This is probably one of the highest priorities, arguably, for nuclear physics right now for us. And there's a very vibrant program worldwide. I think that the neutrino sector is giving this the due attention it deserves. Meanwhile, what are we doing for searches for baryon number violation only? Here, I think we're really underexploring this territory. Now, it turns out it's kind of hard to find processes that don't accidentally end up violating something else. But what you're left with, one of the most sensitive ways to look for pure baryon number violation is actually neutron oscillations, neutrons transforming into its own antiparticle. And this is a topic I'd like to focus on today. So you can treat a neutron oscillation as a mixing of a two-state system. So here we just have a mixing matrix. You have the Hamiltonians of the neutron and the anti-neutron state, and then this off-diagonal mixing term. And so you have to consider what are the potentials that the neutron experiences and its anti-neutron experiences in order to understand how to approach the oscillations. So we have magnetic potentials are very important for neutrons. They have a magnetic dipole moment. And of course, with antiparticles, these have opposite magnetic moments. And also there's material potentials that neutrons can experience. And of course, antiparticles interact very differently with materials. They have this unpleasant tendency to annihilate. So oscillations are actually suppressed unless we can get this energy difference from these diagonal terms to be small enough and much, much smaller than these off-diagonal terms in order to be able to actually see these oscillations. The problem is these off-diagonal terms, based on the limits we already have, are just unreasonably tiny. I mean, 10 to the minus 29, that's just not experimentally feasible to approach. So we have a cheat code in physics. We can operate within the uncertainty principle. And what we can do is use the uncertainty principle to just violate energy conservation for just a little bit of time in order to sneak around this constraint. And we operate in what's called the quasi-free limit. So there are two ways primarily of approaching neutron oscillation searches. You can use free neutrons, which you create and liberate from atoms, or you can use the neutrons already in the nucleus. So with free neutrons, your primary fear is magnetism. Earth's magnetic field is 10 to the minus 18 mega electron volts. So I'd have to suppress this by 11 orders of magnitude if I didn't have this cheat code. Luckily, because typically neutrons in the experiments we build today, we can really only kind of let them fly for about 100 milliseconds before they run into something. That corresponds, that time corresponds to a magnetic field about 10 nanotesla. That's experimentally reachable. And in this limit, as long as we can stay within these constraints, as the longer the neutron flies free, the probability to transform increases quadratically. So it's very attractive to let your neutrons live freely as long as possible, as well as us all. Inside nuclei, you have this completely obnoxious nuclear potential, but thanks to the uncertainty principle, you have bound neutrons can be free very temporarily within the nucleus according to their binding energy for about 10 to the minus 22 seconds. That's a very tiny number, and there's not really any way to get around it. Anytime you're dealing with a nuclei, you have an overwhelming nuclear suppression factor. And the only way to get around that is as many nuclei as possible. And that's why we're happy for proton decay. They built us some really nice massive detectors. So what does an annihilation look like? How do we know that we've detected a neutron anti-neutron annihilation event or an oscillation event? So in nuclei, you're just waiting for the possibility that one of these 10 to the minus 22 second neutron existences has the chance to spontaneously oscillate into an anti-neutron, and being in a nuclear environment immediately annihilates. Typically, you produce on average about 5 pions in an event like this, a couple of charged pions, maybe some neutral pions. There are some interesting features about this kind of event. First, it's a ton of energy. You have twice the mass of the neutron, so that's 2 GeV. Your total momentum should be 0. The origin should be in the center of the nucleus. You should have really good isotropy, just from the kinematics. This should be a really unique looking event. But there are events that can come kind of close to this. One of the primary backgrounds that you worry about when looking for this kind of event is actually neutrino scattering, where you have these very forward directed events. You do produce some pions. You have to be very careful with your cuts and your selection criteria. And so you usually have a pretty low detection efficiency. For example, with Super K, the Super Kami-Hande experiment has produced from their runs 1 through 4, the best limits one in bar today, they had about a 10% signal efficiency. So they only ever saw 11 candidate events, and they expected about 9 backgrounds. And so they were actually able to put the strongest limits about almost 5×10 to the 8 seconds. So it's still a pretty far cry from proton decay. So there's, I think, some room to grow. And with Dune, I'll just quickly mention, you get some nice advantages from the liquid argon CPC with particle ID and these bubble chamber-like images. And so you can make some modest improvement according to their last CDR. Conversely, with free neutrons, you really don't have anything else that's like it. You really can be a completely background-free type of measurement. You're looking for something at a neutron source that's just a tremendous amount of energy, all of these details of the kinematics. You can't produce anything else like it at a neutron source. However, you don't have this Avogadro's number advantage of the massive detectors. So you're really competing with the fact that it's hard to get a lot of neutrons in order to have the sensitivity to see these events. So the last research was actually published in 1994, quite some decades ago. They saw 0 candidate events and they expected 0 backgrounds. And they were able to put a limit at about 1/10 to the 8 seconds. So that's a long time ago. We've learned a lot since then about neutronics and detection capabilities and cool analysis tools like machine learning. I think we can do better. And so that's what we hope to do. So there's this really nice opportunity with both taking advantage, leveraging these great technological advances, and also this new facility coming online, the European Spallation Source, where we were able to get in early enough and be loud and annoying enough that they were actually able to accommodate a lot of our requirements in order to be able to do an extremely impressive new search for neutron, anti-neutron oscillations. So I'll just give you a quick overview. You start by building lots of neutrons. So the European Spallation Source will be the world's most powerful spallation source in the world once it comes online. You need a really good reflector. Ideally, you want your neutrons to be traveling as straight as possible. If the concern is if it reflects off of a wall, it's more difficult to, in the most conservative case, you assume that you lose the event, because if it's an anti-neutron, it would annihilate. You have to restart your clock. There are some ideas where you don't have to do that, but I won't get into that. You want to have your neutrons going as straight as possible through as long a time as possible. So here we're shooting for something like a 200-meter beamline. It ends up being just a little bit shorter in practice. And then finally, you pass all your neutrons through a target. Here we're proposing a carbon target, It's mostly invisible to neutrons. You don't actually get much backgrounds from the neutron scattering in the target. But of course, it's a big deal to an antineutron. An antineutron will annihilate and produce this pion star, which we can detect. And so we just have to be able to track the charged particles, use a calorimeter to detect the total energy of the uncharged pions, use timing so that we can be sure the event was originated in this 100 micron foil in the center, and veto as much as our cosmics as we can. We really should be able to do a background-free measurement, which with much better sensitivity or efficiency than the previous. I think ILL was about 50% signal efficiency. I think we can probably get closer to 80%. I don't know the party line on that, but that's ballpark. Bottom line, if ILL saw one antineutron, this experimental concept would see 1,000 antineutrons. So we could have an antineutron factory, and then you can have some real fun. Now, I just want to point out the way we define sensitivity is different from the lifetime. So in terms of lifetime, we'd be reaching something like 20 times 10 to the 8 seconds. Sensitivity is more of an experimental sensitivity. But because it's a background-free experiment, we only need to detect one antineutron. And so if we detect one antineutron, I think we have a really compelling case that we've done something really groundbreaking. So there's been a lot of exciting activity related to NNBAR in even just the past year. A year ago, my talks consisted of this cartoon. Now my cartoons are 3D. So we've done a lot of engineering studies, and we've developed a conceptual design report so that we can actually have a really clear picture of how to integrate, how to build this experiment, and how much it's going to cost. So we've done one of the most important accommodations that we've gotten from the ESS. And man, I really wish we had this ability in the US as well. But they've allowed the fundamental physics community to design the second moderator. So there's an upper moderator. The ESS is primarily serving neutron scatterers, material scientists. Fundamental physics is kind of an afterthought. But here, we're actually doing a design of the second cold source. This is going to be a much more higher intensity cold source, and it's going to be optimized for fundamentals physics. We're also there's some inclusion of an ideas for an ultra cold neutron source, a very cold neutron source, and there's some potential neutron scattering applications there that are being considered. But really, this was designed with NNBAR in mind, and that's a big deal. Oops, wrong way. Let's go forward in time. Forward is more exciting. We've also, they're putting their money where their mouth is. This large beam port, which is a completely unique feature, and just in general as a neutron physicist is extremely exciting. This is not a beam port. This is like a beam like door. It's more than 3 times bigger than a typical beam port. Right now it has a plug-in, so you can actually see what a typical beam port size is. The large beam port is following the outline of my laser. This is just going to give us a tremendous number of neutrons, which we need because we're looking for something very rare. And we've also done completed a conceptual engineering design. And so that's the beamline, the reflector, the shielding, the magnetic shielding, radiation shielding, and design of a detector, which I show very tiny here. But I should move on because I have a lot more talk to go. Okay. So something that I think, when you go from concept to real actual engineering design, something that usually happens is you lose sensitivity. Here we actually managed to gain some. Unfortunately, the ESS is postponing its 5 megawatt plans. Currently, it's planning to run at 2 megawatts. 5 megawatts is future upgrade territory, which may or may not happen. You know how that goes. But NNBAR the collaboration has managed to maintain that goal sensitivity, that factor of 1,000 in units of ILL sensitivity, even with the ESS at 2 megawatts. So if we do get that future upgrade, we have that possibility for even more sensitivity. Okay. So we know how much it costs. We always thought it would be about an order $100 million or 100 billion euros. So that's 20 billion Mexican pesos. Very, very large scale project. It's very well motivated. But it's a bit far off in the future. It's nice if there's something we can do that's smaller scale, maybe a staged program that can lead us there and let us, approach this a bit more slowly rather than hitting the credit card all at once. So there is some actually complementary science that we can achieve on this shorter time scale. If we look at processes that instead of violating Baryon number by 2, like in bar, violate Baryon number by 1, and these kinds of neutron oscillations. So it's a straightforward extension. If we consider the mixing of neutrons and antineutrons, if you can accept the idea of a dark sector, which might contain something like a dark neutron or something a dark neutron or something a neutron can oscillate into, you can just extend this very naturally and have a mixing among all 4 components of the neutrons, the antineutrons, their dark partners and dark anti-partners, as the case may be. And there are theories that propose this with some connections of cobaryogenesis, where you're trying to generate both the antimatter and matter asymmetry in the universe at the same time as the dark matter in the universe. And interestingly, this could also be a shortcut to get to neutron, anti-neutron oscillations through a dark sector. And I'll talk a little bit about that. But for me as an experimentalist, I think this stuff is kind of neat, but I'm really excited about in and bar. So what I really like about this kind of possibility is now we can have a very timely opportunity to do some of the prototyping that we need for the anti-neutron detectors, the different algorithms that we need to use to select data, and the different types of detectors and how they might integrate into the beamline. These are still kind of open questions that will change our path forward. Okay, so the way we're approaching this, we'd like to get to N and bar, and we've devised this kind of stage program with increasingly complex searches, and I'll talk about primarily one of them here. So we want to look for neutrons transforming into a dark sector, some dark neutron, and transforming back into neutrons under some different assumptions. And I'll primarily talk about this mass splitting one, because these are the experiments we've already been conducting. And I'll just touch on very briefly the further programs. But what I want to say is, we can start with these really easy experiments where we're looking for neutrons that disappear and then come back. Then we can build a more interesting or a more complicated, but potentially more interesting experiment where we're looking for neutrons that go away but come back as anti-neutrons. And that gives us a lot of R&D development. And this is something we can want to do in the high beam program at the European Spallation Source. And then finally, the ultimate goal, of course, we just want to look for neutrons directly transforming into anti-neutrons without needing to believe in these particulars about the dark sector. And so the techniques that we're using, this disappearance technique, is what we call cold neutron regeneration. And so at a high level, basically, we're inducing cold neutrons to vanish, typically with magnetic fields. The neutrons are then blocked by some very strong absorber. If neutrons transform into some dark matter, they won't care about this absorber and they'll just continue along. But we can induce them to transform back into cold neutrons. We can regenerate them, and these regenerated neutrons can then be detected. And so the idea is you look for, as a function of your inducing magnetic field, you look for neutrons suddenly appearing. You're basically shining neutrons through a wall. You're looking for neutrons suddenly appearing when they shouldn't. So there are actually theories that have existed a long time and have predicted these, that you can consider a dark matter candidate. One of these candidates is from mirror matter. This just came from this desire to understand the left-handed nature of the universe. The simplest thing you could do is create a right-handed one. They just happen to not interact. So, okay, that's a dark matter candidate. And our understanding of dark matter has evolved, but the theorists have also evolved in massaging this theory so that we can still kind of meet at least some of the constraints that we have currently on dark matter. But what's interesting for me as a neutron physicist is there is an experimentally testable consequence, which is that if there is a mirror, a twin of the neutron should oscillate into it if nothing forbids that process. And that's something I can search for. So again, it looks very much like the neutron anti-neutron mixing, except the potentials are different. Here you can have some mass difference between the two neutrons if your Higgs Bob is different between those. And you also have different potentials. Mirror neutrons live with mirror magnetic fields and mirror matter and so forth. And we, of course, live in the ordinary Earth. And so this mirror neutron could be experiencing some different environment than our regular neutrons are. And just as before, we really want this diagonal term, any energy difference between these states, to be as small as possible so that we can have this enhancement of this probability to observe an oscillation. So this is a rare process, but here it's actually not background free. None of our techniques are. But what we can do is very carefully measure our background. We can use the laboratory potentials that we have at our disposal, especially the magnetic field, but we could also use material potentials in some models, and tune those to look for a place where we can compensate this energy dependence or energy difference and look for evidence of this mirror sector. So I should probably go a bit more quickly, I think. Or how am I doing, actually? Almost 10 minutes? That's okay, I can do that. Okay, but I'll go just a little bit quicker. So we have been searching, you know, it's not just me, you know, I'll just mention this is a great time for a crackpot question, but other people are also kind of looking for these kinds of searches for mirror neutrons. The first idea to look for them was because there's an idea it could be an explanation of the neutron lifetime puzzle, which I'll talk a little bit about later. And we put in really strong limits, assuming there are no mirror matter potentials, assuming the mirror neutron is just completely in vacuum, and we could just do this kind of search the same way we do it in bar search. We try to perfectly cancel magnetic fields. But when people relax that assumption, they found some anomalies. And so what you're seeing here, these bands are some anomalies that formed and some points that are corresponding to some best fits. And so there's a lot of work now at this sort of low magnetic field splittings to try to rule out this kind of space. More recently, we've kind of been expanded more in our searches and looking for even larger energy splittings. And so all of this is represented in red here. And now there are more techniques, especially in the past couple of years, which are trying to rule out oscillations of neutrons into their hidden partner over larger mass differences. So from 10 to the minus 11, you can see here to 10 to the minus 4, and even beyond with some searches in neutrino detectors like stereo. Okay, so moving toward the program we're focusing on at Oak Ridge, this first stage of the program is actually motivated by this neutron lifetime anomaly I just referenced. So you have two techniques that we can use to measure the neutron lifetime. We have this bottle technique. So you put neutrons in a bottle, you wait a while, and then you see how many are left. And then we have this beam technique. You pass the neutrons through a bottle, and then you try to capture the decay products, and you compare those rates. And it turns out those techniques don't agree. The beam method produces a slightly larger lifetime to the tune of about 4 sigma. So that's a serious discrepancy. You have to pay attention to that than the bottle measurements. And so you can ask this kind of intriguing question. Are the neutrons disappearing into something that isn't a proton? And you can go a step further, maybe even dark matter. So with that, we had a proposal that one of the most precise beam lifetime measurement actually could be experiencing kind of uniquely the neutron oscillations if there was a mass splitting. So here's how it works. So the beam lifetime measurement at the National Institute of Standards Technology, it's a beam of cold neutrons that goes into this trap. If the neutrons decay, we use a combination of magnetic and electric fields to trap the protons, and then we can kind of collect them later and detect them. And so you're comparing the rate that you're measuring protons to the rate that you're measuring neutrons. So the idea is, if there is a mass difference between this neutron and this mirror neutron, it would actually be compensated. If it's low enough, it could be compensated by this magnetic field. And you have this effect that you can sometimes see in material studies, this Landau-Zener transition. You have, when you approach an energy crossing of two states, you have this enhanced probability to jump into the opposite state. And so that's what could be happening here. So what you would actually see happening is neutrons have this enhanced probability to jump into a neutron state. And when they're in that state, they're not going to decay into protons. They might decay into mirror protons. They might be something else and not decay at all, whatever it is. The neutrons are there, the protons are not. The neutrons can then experience another Landau-Zener transition when they go through another energy crossing where the magnetic field compensates this mass difference. And here it jumps back into the neutron state. And so the proton decay rate is impacted much more strongly than the neutron decay rate. And that would actually give you this too long of a lifetime. So this is a very bad way to test. It's a good way to measure a lifetime, not a good way to test for neutron oscillations. And so we just did a simple experiment that was a bit more tuned to look for oscillations, where we put a very strong absorber in the middle of a similar magnet so that we could block any real neutrons, allow these dark neutrons to pass, and then on this left-hand side, only these mirror neutrons would remain, except they transform back into regular neutrons, which we could detect. And so we're trying to shine neutrons through the wall here. So I wanted to give just a little bit, I might go a little bit quickly through this one, but this is just how we calculate this and shows that this, how the Landau-Zener transition actually looks like. And so what we're calculating is, we're just calculating the density matrix of the neutron, whether it's in the neutron or mirror neutron state. Numerically, we calculate as it goes through the magnetic field profile of the beam lifetime magnet. When it approaches this point, so the blue is the magnetic field, the black line is where the energy would be compensated by a particular mass. What we see happening is once we approach that point, we do in fact see this Landau-Zener transition and another transition on the other side. As you can actually see, the red is the probability to be found as a neutron. The neutron would transform into this dark neutron state, pass through this decay region, and has some probability to transform back into a neutron on the other side. And that would give us, basically what we're comparing is the rate of neutrons to the loss in the rate of protons. And we want to look for something that would correspond to the neutron lifetime puzzle, and we can calculate that for all parameter space. So this y-axis is basically it's like a probability parameter. The x-axis is the mass splitting. And so these are the parameters that would be consistent, this in the red, that would be consistent with the neutron lifetime puzzle. So here's how the experiment works. It's a fisheye lens, so it's a little distorted because it's sort of a narrow cave. But this is one of the neutron scattering instruments at Oak Ridge, at the Spallation neutron source. We have a neutron beam coming through. The arrow is actually straight. That's just an effect of the camera. It passes through a large magnet that it's close enough. We can calculate the differences from the beam lifetime magnet. We put a strong neutron absorber, just basically a big block of boron tin. And we impinge we look for any evidence of neutrons on the other side of this absorber, whether or not the magnetic field is on or off. And so what we found in basically all configurations we've tested was we measured the exact same rate. So that was basically, we're just doing a very good background characterization of this instrument. We saw no evidence of any mirror neutrons being produced, but we were also able to exclude a lot of the parameter space, especially this red band, which would be the parameter space that you would need to explain the neutron lifetime anomaly. So we can actually, I think, I can check off my bucket list. I killed the theory. It's every experimentalist's wildest dream. Okay. So we figured out how to do it. We kind of put an experiment together quickly and learned a lot about how to do the experiment. We learned how to do it a little bit better. We've improved our backgrounds in the detector. It turns out neutron scatterers really don't care about backgrounds. They just care about the relative measurements. But of course we did. So we spent some effort to reduce backgrounds. We did a little bit better job of setting up our beam line so we can get as much intensity as possible. We also started to understand a little bit about the consequences of the material. We knew, but we didn't realize until we did the full calculation, we have to take into account effects of how the material compensates the magnetic field in addition, and that it actually creates sort of void regions. And so we just chose a material where the void region was already excluded, and then we can have a bit better, broader sensitivity exclusion region. And so this is our final result for measurements done at the spallation neutron source. In blue is the result that ruled out the neutron lifetime anomaly, and in black is the limits that we've submitted to physical review D, and we hope that after responding to reviewer, that will be published later this summer. And here you can see where we live in the context of all of these new efforts, or these recent efforts, and we're very competitive in this kind of 0.1 to 0.02 nano or 0.01 nano electron volt region. And we're somewhat competitive up here, especially if you go to negative mass splitting, which I don't show because I thought it would be a little bit unfair, but these other experiments lose all of their resonance. And so we kind of peak up above their sensitivity there. Okay, so to do even better and to do even better with our program, we need a lot more neutrons. A spallation neutron source is a little bit more tuned, especially existing instruments. They're really tuned for brightness. So if they throw away a lot of neutrons to accomplish brightness, we just want as many neutrons as possible. So we wanted to go to a reactor. And so we went to the high flux isotope reactor Alfredo introduced earlier in this conference. We get 10,000 times more neutrons than SNS. So that's a pretty big win for us. We also have a better shielding of the backgrounds. Here it's a much louder, I guess, environment because it's a big open guide hall. But so they do a much better job of shielding. And also we have longer beam guides. And so for the kinds of techniques where we want to take advantage, I mentioned earlier, this quadratic increase in probability as a function of time. To take advantage of that, we need the beam guides to be as long as possible. So this is actually, you know, it's a neutron scattering instrument. It's a SANS machine, but it actually works reasonably well for the kinds of experiments we want to do. And so we've taken our SNS experiment, we've moved it to hyper, and in January, we've completed data taking. And so this will be our ultimate, this is very, very preliminary, but this will be our ultimate sensitivity to this particular mechanism. And this is the first stage in our program. You can see how the sensitivity improves by, the black line is the result, the improved result, the last result from the spallation neutron source. The red dashed line will be our result from the high flux isotope reactor. We have more ideas that we want to look for, different mechanisms by which neutrons might oscillate. For example, maybe there's a coupling to both magnetic fields in the off diagonal, a so-called transition magnetic moment. You do see these in other particles. They're hypothesized for neutrinos and so forth. This idea is also proposed to explain the neutron bottle lifetime. So we're prototyping in an apparatus and hope to do some more data taking this at the end of the year. And we're looking for funding for our last stage, which is to do another search for mere neutrons, assuming no mass splitting. And I'll explain that a little bit more here. All of this is to inform the high beam program, which will take these steps to the next level and bring in coupling to antineutrons. They're building a dedicated instrument. I think it's about 50 meters long or maybe just shy. They've done a lot of the engineering studies and have high confidence to get the beam line, but it's still early. I don't know all the details there. But anyway, here the goal is they'll start from our third stage, our last stage, where you're looking for neutrons traveling for a long period in some magnetic field, which is meant to compensate some small magnetic potential that might be in the mirror sector. This is the original oldest scheme of searches people have tried to do. You're looking for neutrons transforming into some kind of dark particle and then coming back, either as a neutron, where you'd have a neutron detector, or as an antineutron, where you'd reverse the magnetic field and have an antineutron detector. And so this kind of scheme, so here in yellow shows the measurement, the landscape, the experimental landscape of limits that already exist, and the potential reach of the different phases of high beam. And so we can go, I should have made that bigger. I think it's like 10 to the 100 seconds. Well, that's what I recall anyway. But anyway, I think the interesting part for us as experimentalists is this is a really good time to do R&D for the anti-neutron detector. Okay, so I think that looking for baryon number violation, we just have to do it. We're putting so much effort into lepton number violation. We have to do baryon number violation. It's important. It's a complementary approach. We can't just pretend it's not there. But I'm really excited about this opportunity that we have in NBAR in the ESS. I think neutrons are a bit underdone, and there's a lot of interesting opportunity there for future improvement, especially, you know, with N-bar, a factor of 1,000, that's rare. So that kind of intensity improvement is not something you come by often. And so it's a very attractive possibility to look for this kind of rare process. And there's been a lot of recent progress in just understanding how to do this experiment, what it would take to pull it off, what are the, you know, what accommodations we need, and making sure that they're there. So at Oak Ridge, we've already used the first stepping stone to this program, a search for neutrons oscillating into, you know, hypothesized mirror neutrons, and ruled out a theory that these could explain the neutron lifetime anomaly. And we have more studies yet to come, some completed in the bag and some that we're planning. And then finally, I hope that this program we do at Oak Ridge can inform what we want to do with the high beam program, which can just, it's dedicated. They can do much better than us, and that's great. And also finally with N-bar. So if I have just 1 or 2 more minutes. So I want to share something kind of fun. You may, in your career, have the misfortune to be contacted by a journalist, as I was, who wanted to hear about why I was looking for something called mirror matter. And so I gave him a discussion, a presentation, not unlike the one I just gave you today, and talked about, you know, how compelling is mirror matter as a dark matter candidate? What are the advantages and disadvantages of these experimental approaches? You know, what are our motivations for pursuing this? I talked a lot about it in Bar. And he produced an article that I thought he did a reasonably good capture of the science and so forth, but he included some language, you know, I'm on the hunt for a universe identical to our own, but split. So it contains mirror atoms, mirror molecules, mirror stars, planets, and even mirror life. It's an innocuous statement. You can imagine the crackpot questions I got at that point. So when another scientist from NBC News contacted me after having read this article, I contacted my supervisor and I said, you know, I'm a little concerned that maybe it's a little bit too flashy. It's not the conservative way I wanted my research to be presented. Maybe I'll just ignore the journalist. No, you should do it, he says. It'll be great. Okay. Maybe it could have been. Maybe it would have been. But then this new TV show came out. So there's a TV show that became very popular called Stranger Things. It's about some high school students who discover a portal to an upside down with horrible, terrifying monsters at a laboratory that really reminds me of Oak Ridge and reminds a lot of people of Oak Ridge. And then the news article comes out. Scientists are searching for a mirror universe. It could be sitting right in front of you. Yeah, okay, that's whatever. At Oak Ridge National Laboratory in Eastern Tennessee, physicist Leah Broussard is trying to open a portal to a parallel universe. I will never forgive my boss. So this completely shut down my email. I'm no longer on social media. I got so many stories, so many interview requests. I was very grateful to the Oak Ridge Communications Department. They were very good about filtering each of the requests. Ancient aliens wanted to talk to me. I said no. But Oak Ridge collected some fun statistics on this. There were about 100, almost all clickbait, but a few really good ones, stories about the experiment. Some of them were, you know, it's a great way to try to find the journalists you can really connect with who are trying to send a positive message about science and not just trying to get clicks. There were just an absurd number of tweets and social media about this. I got letters. One of them was a woman who said she had a haunted mirror that could lead me to the parallel universe, so I didn't have to, you know, build these experiments. She'd sell it to me for $100. It'd be great if I could go pick it up. She's in California. I got some art, and I got a lot of response from the public. About a third figured the media was overblown, but they were really enthusiastic. They were very excited that this kind of, you know, groundbreaking science was being done. And so it was nice to kind of energize the audience. I think maybe we could do a bit better about communicating to how we energize them. Plenty of, I'll say, alternative physicists. Maybe that's a nicer term. And what surprised me was just the large fraction of people who really just wanted to go through the portal. But considering the time, maybe I don't blame them. And so I thought I would just share and leave up a few of the funnier quotes that I've received, a few of the funnier messages. So Leah J. Broussard, have you considered what might come through the portal? Neutrons. Okay, regardless, please proceed. Some of them were really heartwarming. One I really liked. I'm an excited hobbyist sharing with my 6-year-old son and 4-year-old daughter, and we wish you the best. That was really cute. And then and finally, I'll just read one more. I really encourage you and your team to watch Stranger Things before attempting to open the gate to the mirror universe. Okay, well, I'll definitely watch Stranger Things before talking to another journalist, I'll tell you that. All right, well, thank you very much.
So maybe we have to start. Okay, how we make them? Just show.
Oh, yes, sorry, I'm gonna make it over.
Thank you for the excellent talk. The last part was as well very funny. So could you please show again the neutron lifetime measurements? Because if I got this right, the last measurements have uncertainties that are much larger than the previous measurements.
Oh, yes.
So
okay.
is this understood? Because otherwise, if there
Yes.
is some systematics going on, then there is basically no anomaly. So
That's a great question. Thank you for asking. So this is an example of why this puzzle is very important. We're very motivated to solve it. And I just want to emphasize, as much fun as we're having with the dark sector, our primary focus is on systematics. And so the primary way we've been using was this beam lifetime technique used at NIST. There are a lot of different ultra cold neutron experiments, but there really only has been for a long time this one technique for the beam. We need more. So there are two new kind of ideas. I think one might be a bit more reasonable to be competitive. But one is the idea, so here, this is a beam of neutrons and we're detecting the protons. There's another one at J-Park where they're using TPC to simultaneously detect the decay electrons and the neutrons in the same detector, but they've got some work to do before they really understand this new technique. And so at the moment, their experimental error bars are still large, but I think that it's an interesting approach and they have some chance to produce a result that can weigh in. This one is even, actually, I thought the error bar should be even larger, so I should double check that this is the one I'm thinking about. There's an effort to measure the lifetime in space. They call themselves a third technique. It's really technically a bottle measurement, I think. But you're basically looking at neutrons bouncing off the surface of a planetary body and trying to calculate, you can reasonably accurately calculate the flux you could expect. But of course, their systematics are really difficult. So they have some time to go before, but neutron lifetime in space, I mean, that's even more crackpot world than I am. So that's pretty exciting. Yes.
It's certainly an interesting idea. What I don't understand is, I don't know much about baryon number conservation, but I sure know about energy momentum conservation. So you start with a neutron, it goes through a magnetic field, and then the neutron becomes an anti-neutron, annihilates. So you start with 1 GeV and you extract 2 GeV. 1 GeV has to come from the field. And so
you can't use magnetic fields if you're transforming into anti-neutrons. So when if you're doing neutron anti-neutron searches, you actually do need to have a full cancellation of the magnetic field, unless you do this dark sector.
So where is the energy coming from then? Because you start with 1 GeV, you have your neutron coming out of the reactor or your source of 1 GeV, and then it oscillates into an N bar, and then it annihilates. When it annihilates, and I've done this with say the DGS, you see an excess energy because it annihilates.
Yes.
And so suddenly you extract 2 GeV.
Because it's annihilated with the neutron in the carbon nucleus, and so that's where the second GeV comes from. It comes from so it's not the originating anti-neutron. It's the fact that it's the result of the interaction with the second neutron.
Yeah, I have 2 questions. I wonder why in that Hamiltonian you wrote at the beginning, you have there the sort of optical model potential. are you really measuring neutron oscillations or neutron decay? Because I haven't seen anything in your talk concerning, say, the oscillation length or the mass splitting between the two states. Because you see, if they oscillate, the mass of the antineutrino and the mass of the neutrino should not be the same.
Our lengths are extremely short. So we're talking about meters. The neutron decay is like 15 minutes long.
No, I mean, your Hamiltonian should be relativistic. I don't see it. I mean, so to conserve angular momentum there and to speak about oscillations, what you need is a base of states. They are mixing up by a certain currents. Then you write it down and you get the probability to oscillate from one state to another. That probability is a function of the amplitude of the mixing times the square mass difference between the states divided by the oscillation length, period. This is how quantum mechanics tell you if you are oscillating from one state to another. The Hamiltonian you write there was diagonal, and the first line goes having P plus or minus IW. So that means absorption, no oscillations.
I might have to ask you offline. I'm not sure I understand the.
Excuse me?
I don't think I understand fully the question.
My question is, if you want to explain oscillations, and
Okay.
you want to measure oscillations, like you do in neutrino oscillation, okay?
Okay,
So you go from one, say, mass ion states to the flavor ion states. You have amplitudes and phases. Very elementary theory. Now you say, if I emit a neutrino in the flavor, say, muon, and I detect that in the flavor electron, or I am missing fluxes, then I presume there is an oscillation in there. When I write down the probability of the oscillation, it's coming out to be the 4 amplitudes times the square of the mass differences divided by the oscillation length.
so, okay, I would have to pass on, I guess, more thorough documentation. This I meant to be kind of a high level overview.
So maybe we can. There was one last question.
Yeah, so let me make it maybe a comment rather than a question because of time. So the oscillation of the neutron into the dark sector as a solution to the bottle versus beam experiment has been proposed before. And then, believe it or not, one of the conflicts are in neutron stars, because if you convert neutrons into some dark sector particle, you'll lose enormous pressure support, and then you will not be able to support these very large masses that we have seen already.
Yes, let me think. We do evade the neutron star limit. Let me think about why. Maybe I leave it for a comment, but I know the answer to this, but I have to think for a minute. Okay, then I'll come back to that.
So let's thank our speaker. Yeah.
Okay, good.
Okay, so our next speaker is Oscar Naviliat from Michigan State University. He will be talking about improved search for CP violation in ortho-positronium decay. So,
Okay, so before I start, thank you, Rudolph. I don't see Maria Esther, but thank you, Maria Esther, as well, for the kind invitation, and thank you, the organizers. It's a pleasure for me to be in the symposium again. I missed the Costa Rica one. So, as you see, I will be talking about an improved search for CP violation in ortho-positronium decay. Our collaboration is huge, as you can see. Elizabeth and Paul, they are from Wittenberg University, and Tomerik Haugen is my PhD, my grad student, and I mean, he deserves a lot of credit of the things I'm going to talk about. So let me start by let me start by making put the context of CP violation. We didn't agree with Leah about what image to show. But we know a number of places where CP is violated in feces or could be violated. So we have the signature of CP violation in the K and B meson system. We have not an explanation, but a description of that through the CP violating phase in the CKM metrics. We have another, say, proof of the CP violation is the dominance of matter over antimatter through, of course, the Sakharov conditions. There are sources where CP could be violated, like the theta term in the QCD Lagrangian. And we have also the neutrino mixing matrix that has a similar mechanism than the CKM matrix. So, in fact, there so happens that we have too much matter over antimatter, according to the standard model. And of course, there must be new mechanism of CP violation that had to be at work in an earlier phase of the universe. Now, last Sunday, I had a very nice discussion with my compadre and great colleague, Gabriel Lopez Castros from Silverstaff, and he was asking me, do you have a recent, robust estimate of what this standard model is actually, how far it is? I found some papers that tell that there are 17 order of magnitudes. What I cannot tell, I cannot tell you or answer you your full question is how robust these estimates are. But let's just don't stop the show right now. Let's move on and say they are robust enough so that we can search for those sources. Oh, sorry. So there are a number of sources, or at least tools we have in order to test CP violation. One of them is EDMs. In fact, EDMs are T-violating observables, and through assuming CPT invariance, we then probe CP. Here's a roadmap that shows on the left-hand side what are the experimental sources to where we get, in fact, inputs from EDM of the neutron. We had talks yesterday, or EDMs from leptons. And on the right-hand side, how we go to the fundamental theory, starting from those measurements. Now, we are dealing here with leptons, and there is here an input from atomic theory. It's not, so this cartoon is not exactly, we have to take it with a grain of salt because this assumes, in fact, that we are making, for example, an EDM measurement of the electron in an atom. And then, of course, that particular method receives input from the atomic theory. It is interesting because then you can probe a number of mechanisms different than a pure lepton. But you have to imagine that, for example, if we have muons in a storage ring and we can deduce the muon EDM from that measurement, there is no such an input. Okay, so we have to really take that into account. So I will be dealing here with leptons as well, but as I said, it will be a different source for CP violation. The other source, the other way or the other tools we have to probe CP violation are through, decay processes. Once again, these are T-violating terms that occur in those decay processes, and through CPT, they will then probe CP violation. So, for example, I took here two examples. There are many of them. I took two examples for semi-leptonic decays. This is, of course, absolutely biased because I took part in those in this experiment. This is a measurement in lithium-8 decay. So you have the beta decay Hamiltonian, you have the initial state, final state. You integrate that over the phase space, and you integrate more or less. For example, if you do not integrate over the electron spin, and you do not average over the initial spin of the system, you can get then in the decay rate, a term which is like this, which appears with a triple correlation. So that was a measurement that we did at PSI in the lithium-8 decay. The arrangement, of course, of the experimental setup is such that you maximize the term. The three vectors is a mixed product. So you have the spin, the momentum of the electron, and the momentum of the spin. They have to be like this so that you maximize the sensitivity to what you want to probe, which is the R coefficient. In a similar way, you have here the neutron decay. For example, you do not integrate over the neutrino variables, but you can integrate over the electron variables. You can end up with a term like this in the decay rate. This is called the D coefficient. Again, the R or the D coefficient. This is jargon in the formalism of Jackson, Treiman, Weil of the 50s. Okay. So this is an experiment in neutron decay. You do not measure the neutrino directly, you measure the recoil. That was done at NIST, and basically one can constrain this way this D coefficient. There are also experiments in muon decay. That was an experiment that took place at PSI many years ago. This is very similar to this R coefficient. But again, this triple correlation probes a term which is similar to this R, which is in the jargon of Fetcher and Gerber, which actually parameterize the muon decay. It's called PT2. Okay, but it's probed again. You maximize the muons are implanted in a target, and then the positrons are emitted perpendicular to the muon spin, which actually precess. And you can then measure by annihilation in flight the polarization of the positron, which was emitted. Now, I want to make, before I move to positronium, I want to make a remark concerning these measurements. And this remark, for those of you who were here on Monday, is connected with the comment I made to our colleague, Professor Moscow from the JPET collaboration, where I mentioned an objection that we made concerning their claims about CP violation using the JPET detector. The two comments I would like to do, which may sound trivial for some of you, is that, as you can see, these triple correlations involve only kinematic vectors that effectively, of the particles that effectively take part in the decay. I repeat, these triple correlations are momenta and spins of the particles that effectively take part in the decay. Sounds like trivial, right? The other one, another statement I would like to do, is that, like an extreme thing, the triple correlation per se, or the triple correlation itself alone, is not probing any physics. The physics is on the term that this correlation enables us to access. The triple correlation is our tool, is our toolbox to access the physics. For example, the R coefficient in this experiment is very often interpreted as looking for an interference between a tensor coupling, this is a gamma-stellar transition, a tensor coupling, which is exotic, and the axial coupling. That's a way to interpret the physics. This experiment, the D coefficient, this is in fact a P-even correlation. The D coefficient in a mixed transition is very often interpreted looking for a mixture, an imaginary phase between the two standard couplings, the vector coupling and the axial coupling, and so on. The PT2 can be interpreted in terms of Michel parameters, which are imaginary. So there is where the physics is. I stop here, more, if you wish, in the poster after this presentation. So let's move now to positronium. Positronium is, again, is a bound state of a positron and an electron. If it is formed in the, singlet state like this, it will decay into 2 photons in 125 picoseconds. If it is formed in the triplet state, as far as the spin is concerned, it will decay in 142 nanoseconds, way longer. This makes that it is possible, it's very easy, in fact, to distinguish these two states by time spectroscopy. So we start a detector that tells us when the positron enters matter, and then we have a photon detected, and we stop the clock. So you see that it's very easy to distinguish the singlet, which is very prompt, from the triplet. And in this case, the 3 substates are degenerate because I don't apply any magnetic field. Okay, so this is a no field measurement. That's a simulation I will show you spectrally later on. So now, what are the different sources of CP violation in positronium? So something that is special with positronium compared to the decay I showed you before is that positronium has well-defined states for, well-defined quantum numbers for parity and charge conjugation. So these are CP eigenstates. The thing is that in contrast to EDMs and decay correlations, we can look for direct searches for CP violation. Means what? Means, for example, remember that the pseudo positronium, the singlet state can only decay to 2 photons. If it decays to 3 photons, it's violation of CP, because in the final state we have CP -1, whereas we had CP1 at the beginning. Same is true for ortho-positronium. In the triple state, we have CP minus 1, if you have 2 photons in the final state, that's a direct thing. And we are from the R number of limits on this thing, and we are now updating those to adapt into direct CP violation. What we are dealing here is indirect, but not in the sense of the CPT. It's indirect compared to this. Okay, so we're dealing with a contribution to the decay rate of positronium, which is directly CP violating. So here it is. Which are the form factors? The form factors in the jargon of Bernreuther, Mahle, and Nachman are named C4 and C5. It's just a jargon. Remember, these are the equivalent of the R and D coefficient of Jackson, Chapman, and Weil. And this is the reference. And the interesting thing is that these terms, if they are present, they do not have, they cannot, there are no mechanisms that can mimic a signature of CP violation, unless, of course, they also violate CP, which is good. I mean, this is a very clean signature for CP violation. Now, which are the correlations that drive these coefficients? Well, it so happens that if you have a polarized source, you have a quantization axis. If you just then make the triple correlation along to project it along this axis, you have this is in the 3-photon decay, the momentum of the highest energy photon. This is the momentum of the next highest energy photon, and you have the perpendicular to that decay plane. So when you have this quantization axis, which as you will see will be given by the magnetic field, we make a projection of this vector along this axis, K1Z, and NZ, which is perpendicular to that plane, along the same axis. And all that is proportional to the tensor polarization of positronium. And the same is true for the second term. Okay, this term is driven by that one, and this term is driven by this one. Okay, so this is in fact how we can access those terms. Now, the properties of these coefficients, and this is important to interpret the previous results, is that they are absolutely intertwined. You cannot get rid of one by making a clever experiment. They will always come together. And you can see in the fact that you need, in fact, the perpendicular, which is determined by each of the two vectors. The other one is that they obey general properties. This is, in fact, by the interchange of photons, that if you interchange the photons in the first term, you get the minus sign of the other one. This is a model independent. It's just, there is no model here. It's just how these terms behave. And the third one is that if you do an experiment and you set one of these terms to 0, for example, this one, and you say that this term C4 is a constant, there is no justification to do so. Basically, you may be, I don't know how this comes. I say that because that was how the previous experiments were interpreted. So let me tell you, no, I said before, these two terms are driven by the tensor polarization. So we need to produce tensor polarized positronium. How do we do that? Well, before, remember, so I have 3 populations of the triplet in the 3 substates, N plus, N0, N minus. And then we, just to remind you, a vector polarization basically tells us what is the difference between populations of N plus and N minus. And it can have values between -1 and +1. But what we need is the tensor polarization, which is this thing here, which actually measure how the population of N2, actually 2 times the population of N2, differs from the sum of the population of N1, N plus, and N minus. And this object here can have values between -2 and 1. They are related, but of course they're independent. We can have one without having the other one. If we have the 3 substates equally populated, we don't have any of these. This is vector 0, tensor 0 polarization. If we have equal symmetric population, then there is no difference between N plus and N minus. There's no vector polarization, but the M0 state is completely depleted. So we have a tensor polarization. Here we have the population of these states is just 1/2 of the population of that state. So there is no tensor polarization, but we do have a vector polarization. In this case, you can have both. Okay, so basically, we can have one without having the other. How do we produce tensor polarization in positronium? So remember, when we have no magnetic field, the three substates, m equal plus, +1, 0, and -1, they are degenerate. So you crank the magnetic field, and then there will be a phenomenon that the two m equals 0 states will mix through hyperfine interaction, and then this mixing will produce two new substates. We are calling this pseudo-triplet and pseudo-singlet. And this pseudo-triplet, basically, you remove that state from the long tail. It gets a much shorter lifetime. So if I look at this region here, I have no m equals 0, almost no m equals 0 state. So this I have basically put the population of that state to 0. It's a little bit more complicated because in addition doing that, we have 3 photon to 2 photon efficiency that come into play, but that's essentially the main idea. So here is a number of spectra, positronium decay spectra. I was involved in all these projects a long time ago, but in fact, it is not so common to find spectra where you do see decay in magnetic fields. So these are thesis 1997. At the time, in fact, the idea was completely different. We were testing parity violation in the weak interaction and using positronium as a tool to probe parity, because that particular state, which I say this is pseudo-triplet, is sensitive to the direction of the incident positron vector polarization, to the helicity of the positron. So here's where you see how easy it is to form positronium. This is a magnesium oxide powder for positrons coming from indium-107 decay. And you see that when you put an aluminum stack, there is no positronium formation, and you have a very nice distinction. Here is we compress this powder to very high density to make the stopping range very small, 1.2 gram per cubic centimeter. And you see also there is still a very clear signature of the magnesium. So when you replace a magnesium oxide powder instead of aluminum plot. And here is this is 1.2, this is 0.6 gram per cubic centimeter of a magnesium oxide powder. So these, in fact, these are theses which are, you have to have the thesis. This is published, although the pictures here come from the thesis. And you see clearly here that component out from the triplet decay, which gets, in fact, decays almost as it was in vacuum. Excuse me. So again, just to tell that it is feasible, I'm sorry, it is feasible, and we have done that in the past. So let me now go back to the previous experiment. There have been, in fact, a number of experiments in this sense. This one is interesting because it gives us the main input. What do we need, in fact, to probe CP in ortho-positronium decay? The experiment was carried out in 1991. There's a group from University of Michigan, neighbors from Michigan State, and they have a setup where they have one detector here that detects the highest energy photon and two detectors that detects the next higher energy photon, K2. And they were making coincidence between these two and comparing that, making an asymmetry, comparing that with the coincidence between these two. And they were, in fact, measuring that one after the other. So they were sequential measurements, probably because they had only one single tag, or I don't know what it means. It's something that today you can easily do. They use only one detector configuration, that's the minimal configuration you can have, one in order to form an asymmetry of counting rates. And the magnetic field was fixed. These are permanent magnets with a very massive yoke that actually fix the magnetic field. They quote here 1.5%, but as I said before, they give a constant. I told you earlier that there is no trivial way how to go from this thing to the previous, say, formalism that it basically established what are the different ways to interpret CP violating signatures in positronium decay. I find this paper is very nice because it gives the main ideas. We cannot blame them because they made the experiment before the theory paper comes out and they analyze carefully, okay? They also do another error which has to do with the tensor polarization, but that's a different thing. Then there was later, that is in 2010, another experiment by a group from Tokyo, where you have here one detector and two in coincidence with these two, or this detector in coincidence with these two. So basically they just double the number of configurations. But on top of that, they put the detectors on a table. They rotate the table in order to have the projection relative to the magnetic field that is changing. So they quote here a value which is 2 per mil, basically an improvement by a factor of almost 10. They use also a fixed field. They use 2 detector configurations, and they took 6 months to do that measurement. Okay, so if we interpret wrongly our results, what we want to do is to improve that by a factor of 10. Okay, but so our goal is the following. We want to improve the statistical. So yeah, again, so this is in fact statistically driven. I mean, it's just dominated by statistics. So we want to improve that by an order of magnitude if we put ourselves in that scheme, which is looking at the next digit, but it's even less than that because we guess that the current digit is 0. Is more like saying, is the next digit also 0? So the next one is that we want to reduce the systematic effects by a factor of 3. We will measure several configurations simultaneously, so measuring asymmetry simultaneously. We will use a tunable magnetic field without yokes, that is in a permanent magnet. And then we will build a highly symmetric, we are building a highly symmetric setup to further control systematics. So here it is, here's the beast. That was the main idea. So we have, for example, remember that you need 3 detectors to make asymmetries. You have the green detector there, and these 2 red detectors from which you can form asymmetries. But we make a setup where you have also possibility to form asymmetries with the 2 blue ones. And then you multiply that by 16 to increase the, say, the angular coverage. So we have 16 here. You can play the same game by putting the highest energy photon on the back ring and having the lowest or the middle energy photon on this side. And on top of that, we have the middle energy photon here and the highest energy photon there. Remember that these 2 terms always occur simultaneously. So we have then 32 asymmetries for the outer, so it's 16 times 2 because we have the red and the blue. We have then times 2 is the additional 16. We have then, in addition, we added a central ring that enables us to have asymmetries which they don't have the, say, golden, we say, the highest analyzing power, but they contribute to the statistics. So at the end, we have, in fact, 257 sets of sensitive configurations to both the K1 or so, C4 and C5. And the central ring, in addition, gives us an additional arm, basically, not only to add the statistics, but to control systematics. Because if both photons are emitted there, we have 0 signal. So it's another way to say that is another control of systematic effects. Now here is a number of, I will not go into details, but this was done during the pandemic, could only do design and what they call simulations. So that was much of the work done by my grad student and at Wittenberg, basically testing the different effects that could arise. I will only, so it's just scattering from the formation source, taking into account the size of the source, taking into account the detector resolution. For example, this plot shows you how the fact of going from the point source to the extended source where the positrons effectively stop, it makes the signal to be smeared out. Or how going from no convolution, assuming a delta function for detectors to some convolution, basically also smear. We have, in fact, something which is more like this. And the numbers there is basically how it destroys the sensitivity in terms of the counting time, which is not big deal. It's just increasing by 5%. The only thing I want to insist is this one here, disadvantage of adding shields between the ring. Because as you showed there, the detectors are very nearby. So you can worry about quantum scattering on one, detecting the other. When these occur on the same ring is easy, actually. But of course, you may say, well, we could add additional lead or brass shields between the rings to avoid that. The result is that is a disaster. You actually increase the number of quantum scattering on the lead shield. And then we say, well, no, we better actually try to identify actively by measuring those events. So here's the beast. We have then, this is the little ball of 48 detectors. These are lysocrystals. They are read out with silicon PMs because we are in a magnetic field. That's the structure. Again, that was occurring during the pandemic. We could discuss with the mechanicians, with the design engineers. They go inside this magnet, which is available. It's a worm bore of 22 centimeters. So the detector is this size. It's like a soccer ball. And of course, the detectors have to be, the support tuned very, in such a way that they get very close. So there's a very high precision mechanics that you need to fulfill. So we designed this. Then the central module, which is the start module, consists of a positron source, sodium or gallium, so germanium gallium, then a very thin plastic scintillators, and then some light guides in order to bring the light outside from the magnetic field. And behind that, you have this positronium information medium that I showed you before, how you can clearly see the signature of positronium. And we are going to use both. In fact, sodium has the advantage that we can tune the setup with that source. Gallium has the disadvantage that has no strong gamma ray instead of 1.2 MeV from sodium, but it has the disadvantage that the lifetime here is much shorter. So we have to change the source from run to not run. We were ready to start fabrication. We spent 1.5 years with discussing with the engineers, doing Monte Carlos. We had shaped the detectors, the best source. And my colleagues say, well, we can order all the 50 crystals. Say, well, maybe just order 1 or 2 to make tests. So they ordered 1 to a Japanese company, a Chinese company. And they put the detector on the silicon PM. They put a cesium source. And depending where they put the source, you put the source on the side, you see this thing here. You put the source on the front, and you see the red spectrum. And we said, well, stop fabrication. I mean, don't trigger fabrication because we have no idea what the hell is going on there. So of course, you know what you should expect from cesium spectrum, right? It's just a clear, nice peak, and eventually a quantum edge. So we knew that, we knew that, of course, if you have large crystals, you have a focusing effect. It's something that is well known. The light, in fact, in contrast to, say, cuboid crystals, get a higher angle, and then you may get some so-called geometrical focusing effect. That is, the light that you get depends very much where you locate the source, because you can have different reflection angles. This is in particular when you rely on total reflection. Now, but on the other side, I mean, we really say, well, no, this cannot happen. It's just 8 degrees. We just did what like this. It's very small trim, you know, it's very small effect. And on the other side, well, we started to blame the Chinese company about the doping. Said, well, no, but over 3 centimeters, cannot be a very big difference in the doping. So I told my student, well, we are going to buy a just cuboid. You measure first, we cut it with the crystallographic lab, they cut it, and we remeasure then the different things and try to solve the thing. So that's what we did. So we started with a rectangular, which is the blue curve. This is in fact sodium source, it's not cesium. We asked our colleagues from the crystallography, please cut the crystal, just take out part of the size so that we trim like this, and we get then the cut is the unpolished, just after you cut, is the red thing. You already start to see distortions compared to the peak. And now you polish that, okay? We ask the technician to polish the crystal, and you get these black thing, which is of course very similar to this thing here. Again, we did all, Tomei did all full position dependence. And then now, after that, what was done is to start painting, maybe basically to add a reflector that reduces the total reflection and in fact enhance the diffusion. And then by doing that, we recover in fact the blue curve, which is the curve that you expect from a rectangular shape. After that, we say go, we can trigger, you can start building the setup because we understand what is going on. So here is a prototype. Good, thank you. Here's the prototype setup. Remember, with only 3 detectors, you can do the experiment. Of course, we are building 48 with, to have 250 configurations. This is detector for 1, and these are the 2 other detectors. This is the, in this case, with a sodium source, and the star detectors were not read out with plastic, but with the silicon PMs, just for test. So this is in fact what you see. If you, in fact, that's the energy in module 1, which is this one here, when you impose different conditions. Here is, in fact, we do a double coincidence with any of the other 2. So this is coincidence this with that, or coincidence with this with that, by ignoring the star detector, which is hidden here behind. Okay, so we don't know where and what you see is this thing here, which is in fact the intrinsic background of the LISO detector when a beta particle stops here and the gamma of the intrinsic reactivity of LISO is actually being detected here. So this is a measurement of the intrinsic reactivity of the neighboring detector. If you impose to this spectrum the condition with the star detector, then you clean up and you see, in fact, the 2 photon peaks, which is, in fact, something that is a triple coincidence between this detector, that detector, and the star. And the other nice result, of course, it's not a big revolution, but it's good to see that. Remember the Monte Carlos. So you see this banana, which is the signature of the 3 photon decay in the energy of the one detector, energy of the other detector here, and which is being shared for this, when we impose, in fact, here a time cut on the long decay source. That is, this is where the 3 photon decay occur. The other one is, of course, a time cut around the prone pit, where you only have the 511 decays. This is the 2 511 decays. So just another word about the intrinsic reactivity. So these LISO crystals, they are made of lutetium. Lutetium decays. Typically, it's about the size of this. For the 3 centimeters and 2, you have 3,200 counts per second. And the nice thing is that we can, by making coincidence between 2 detectors, 2 neighboring detectors, and gating, that is, we say, well, let's assume that the beta particles is detected in one detector. What is the other detector seeing? This is shown here. It's similar to what I showed before, but having a more careful cuts on one of the detectors. And basically, it gives us, I have to admit, it was not designed like this, okay? It's like a sort of, we get it for free. So it gives us the position of these 300 kV, which is there, 200 kV there, and the 80 kV, so that we can monitor the stability of the device, not continuously, because we need to put different gates, but in fact, we can do that routinely. In fact, it's something that we can measure almost simultaneously. Now, I talked about the asymmetries. Now, those of you who have measured asymmetries will not believe that I will be able to measure these at the 10⁻⁵ level. So how do we get there? And what enables to get there is, in fact, the tensor polarization. Remember that the signal is driven by the tensor polarization. And the nice property is that we can form then at different times, just taking different times during the positronium decay, we form asymmetries from all these the counting rates in one detector, one coincidence, compared to the counting rates in the other coincidence. But the tensor polarization, depending on the magnetic field you set, can vary. For example, let me take here, that's for different magnetic fields. I take 0.3 Tesla, so this green curve, it varies by a factor of 10, okay, by an order of magnitude between the beginning of the decay up to the end of the decay. So not only we can switch this signal on and off, but during the measurement, we have 256 configuration asymmetries that they may have their own offsets, but they have in fact, to show the same signature, which is the one that is shown here. So that is how we basically cancel many systematic effects. So I will stop here. I lead you with the summary and the timeline, and I thank you very much for your attention.
We have time for a couple of questions. Is there any question?
Thank you very much. Since I was mentioned, I would like to comment. It's very nice experiments, what you are doing, but I would like to refer to the comments which you addressed to our work. Could you please show this page with that statements? Because these statements are not about our experiments, but these statements are about the other experiments which do not imply anything about what we are doing. We have invented a different method. And from that statement that the triple correlations only involve kinetics of particles which to take part in the process, this is a true statement. But it has how this statement tells that what we are doing is improper. And the other statement is that correlation drive okay, I cannot reach.
Correlations drive
Okay,
coefficient that contains the physics. The correlations themselves don't contain any physics.
And I agree, this is again a truth statement, but it doesn't tell anything about what we are doing. We have invented a different method. And the method is based on the measurement of the momenta of the from the decay of photons from the decay of positronium and their polarization related values. So there is a polarization, which is another parameter, which is not used in that experiments. And what we in fact are doing, we look for the scalar product, not a triple coincidence. At the end, it is a triple coincidence, but this is a tool. It is a scalar product of one of the momentum and the vector of the polarization plane oriented to the polarization. Oriented, we can say normal to the oriented normal to the polarization plane. And in all these previous experiments, polarization was not measured. And the triple coincidence is to measure that vector connected to the polarization. It is not the property, as it is stated here, of that third photon, which we measure, is not coming from the ortho-positronium, but this photon is used to measure, so this is a tool, the polarization related value. And in the end, what we are doing, we are looking for the symmetry odd correlation, which is based on the momentum of the positronium and the vector in the polarization plane. So this is what we are doing.
Thank you for the comment. In fact, as you could see, I have totally ignored, I do not ignore your work, you know this, but I have ignored, I did not want to address that thing here during my presentation because it will be too long.
Okay, but
and that's the reason why I have prepared a poster and I invite everybody to go there and discuss that in length during the poster session.
This I can understand, but maybe it would be fair to tell what is wrong, so I can refer to that in audience.
I'm sorry. The claim, I maintain all these claims, and I maintain that one of the vectors that you are measuring, the K2 prime, does not verify the first condition.
Yes,
We
but
can
it doesn't
discuss,
matter.
please, we can
because
discuss that after.
Yeah,
So-
they are not only triple coincidences, but there is also a scalar product of the vectors, which may be a measurement for the CP symmetry. So I think it would be fair if you tell what is wrong, and I can refer to that.
We present our arguments in the poster, and I would appreciate that you
thank
tell
you.
us what is wrong.
Thank you.
Thanks for the comment. Is there any other question? If not, we thank, oh, sorry. Sorry.
Hi, could you explain why did you choose LISO crystals instead of other? type
Oh,
of
very good
detector?
question. I mean, in fact, I think I wrote that is a sort of compromise. We were of course including a number of crystals because we excluded all what is hygroscopic or slightly hygroscopic, okay? And it's, for example, it's cheaper, of course, if you buy sodium iodide. But of course, if you want to have them in small shapes and couple a silicon PM. So we had another choice would have been YAP scintillators, but YAP is way more expensive. So at the end, to build, I mean, just a crystal which is 2 × 2 × 3 today is about $400. So it was a trade-off. We had to leave. It was enough for, say, peak to Compton efficiency, but basically the trade-off was to pay cheaper, but we had to leave with this background, with intrinsic background. But at the end, it's good that we have the background because then we can monitor the stability. It gives, of course, a single load all the time of about 3,000 pounds per second. Thank you.
Okay. Well, let's thank our speaker again. Okay, so our next speaker is, oh, I don't know. No signal. Yes. Okay, so our next speaker is Dinko Poo'cani. I hope I pronounced that correctly, from the University of Virginia. He will be talking about precision studies of neutron beta decay with NAB and PNAB. Thank you.
Thank you very much. It is a great pleasure.
Use the microphone. All right. It's a great pleasure to be at a LASNPA again. After many years, I was last time at the one in Quito. Unfortunately, I also missed Costa Rica for reasons beyond my control. So I'll talk about the our program of measurements on the neutron beta decay, and because this is a meeting that cuts across a broader cross-section of nuclear physics, and there are a number of students in the audience, I'll give a sort of a gentler introduction, for which I beg the indulgence of my specialist colleagues for the sake of the non-specialists. After the motivation, I'll talk about the principles of the measurement of the NAB experiment and the status and our plans for NAB, and say a few words about PNAB as the extension of NAB and its importance, and we'll look at where it all leads eventually. So I have to get a grip of these. So the story begins with quark lepton universality in beta decays.
if we look at the basic weak interaction V minus A form, which has been known since the 1950s, the matrix element of a vertex involves a term with the leptonic current that has only the vector and axial vector terms with opposite signs. It is perhaps miraculously replicated almost identically in hadronic weak decays, where we have the very same type of form for the transition. So here we go from electron couplings for electrons and neutrinos, and here, say, proton and neutron, or up and down quarks. We have the same vector and axial vector form with factors that are very nearly one. And in fact, initially, the first one was believed to be one until in the 60s, Capebo showed that, in fact, there is a mixing angle that makes that into a number that's slightly smaller than one. It's a cosine of the Capebo angle, which is about 0.97. And axial vector current, so the reason that that's true is because, of course, the vector current is strictly conserved. The axial vector current is not, and therefore there's a number which is slightly different from one. This scheme was generalized into 3 generations of quarks by Capebo, Kobayashi, and Masukawa, and instead of one angle, we have several, and there's also a phase for CP violation. So the CKM unitarity condition tests the sum of the squares of any row or any column in the matrix, and the one that can be most precisely evaluated is the first row. And the tests of CKM unitarity, which of course means how closely does this view of weak interactions in the quark sector mirror the nature, the actual state of affairs. That's been the best available test. And until 2004, roughly, it appeared to be violated in excess of about 3 sigma. But then our colleagues in the kaon sector discovered that there were actually corrections. That one experiment pointed out that, in fact, there was a need to reevaluate, and a number of decay results were reevaluated, and that disappeared. Since then, that's been an area of shifting ground, and we'll see that in a moment. So the Lagrangian then has this form for that involves the VUD matrix element, which we can combine together with the Fermi coupling factor GF into a GV, the vector coupling constant for the hadrons. And we also have the lambda, which is the ratio of the axial vector to the vector coupling for the neutron, for the nucleon. That's the part of the hadronic current, and that's the leptonic currents. Those are the 2 vertices. How well do we know these? The Fermi coupling constant is known incredibly precisely, for our purposes, infinitely well determined. And the lambda, the ratio of the axial vector to the vector coupling, is about 1.3 negative, and that's best known, as we'll see, from correlation measurements in neutron beta decay. And the rate of the neutron decay, or its lifetime, the inverse of the lifetime, is given by a combination of these factors. So GF squared we know really well. VUD and lambda need to be determined. So if we want to evaluate the VUD from a known neutron decay rate, we also need to know lambda. So 2 parameters are needed. So therefore, if we invert that expression, we get a numerical condition which tells us that in order to find the proper solution for GA and eventually VUD, we need to find the intersect of this ellipse, which is defined by the constant value for the neutron lifetime, so therefore measurement of the neutron lifetime, and we have to know the slope of the GA versus GV. In other words, the ratio of the two, and then the intersect of those two lines. The line and the curve will give us the solution that we require to find VUD. So the questions here are how uncertain are the ellipse and the lambda sloped line, and how reliable and consistent are the results from different methods of evaluating the neutron lifetime and the ratio lambda. And in fact, we had quite a bit of a taste of that in the first talk, which talked about where Leah discussed the differences between in-flight and bottled measurements of the neutron lifetime, and we'll come back to that in a moment. So the neutron beta decay rate, this is the double differential beta decay, triple differential beta decay, is proportional in lowest terms. There are many others, and we saw some of those terms that violate parity. The lowest terms allowed that are consistent with Lorentz invariance involve a electron-neutrino correlation, a distortion little b of the beta spectrum, and then correlations with the spin. So these are unpolarized neutron decay parameters, and then a bunch of polarized ones. If we step in with a standard model that prescribes that the distortions of the spectrum, little b, they are strictly zero. If they were not zero, then they would signal presence of scalar and tensor interactions, which are, of course, excluded in the standard model. And furthermore, the standard model says that these parameters, little a, big A, and big B, are related in a very fixed way, prescribed way. They are related with the parameter lambda, which is this GA over GV. So measuring some combination or certain of these decay parameters gives us access to lambda. When we combine that with independent measurements of the neutron lifetime, we can get access to CKM-VUD, which is the leading order 1 term, and its uncertainty then dominates the uncertainty of the evaluation of the sum of the squares. One can also look for the proton asymmetry, which is a combination of A and B terms. Now, in a situation like this, the standard model over-constrains these A, B, and capital B observables in the beta decay. And so if we find that they do not follow this prescription, then in fact, one of them differs from the lambda dependence as is prescribed by the standard model, that would indicate presence of right-handed currents. Or if we detect these Fields interference coefficients of little b to be non-zero, this would again lead us to limits on scalar and tensor terms. So how well are these known? Up until a few years ago, this was a shorter list, but there's been a lot of activity. We're going to focus on the first term, little a. That's the A in the NAB experiment. That's in electron-neutrino correlation. And NAB proposes to measure this with a relative uncertainty of 10 to the minus 3, or approximately almost an order of magnitude better than it's been known so far. And there are two recent results from ACORN and Aspect, which have vastly improved the previously rather poor precision on the experimental studies, and we'll see that in a moment. Little b, we wish to measure with the uncertainty of 3 times 10 to the minus 3. I'm not quoting this, of course, as a relative error, because uncertainty, because it's the expectation value is 0. And there are only very recent measurements of this. And in fact, some are slightly inconsistent, but that addresses a deeper question of the interplay between PKO3 and aspect results. NAB, as we plan, will be followed by the polarized version of it, PNAB, which measures, actually focuses on capital A and also evaluates the B or proton asymmetry to 10 to the -3 relative precision. So, as I've said, the motivation is to have multiple independent determinations of alpha. We do not measure the neutron lifetime, only the axial vector to the vector coupling constant ratio as contributing to the test of CKM unitarity. And we expect to have independent and competitive limits on non-standard model currents beyond the standard model. So what is the current status of these limits? So let's first look at the CKM unitarity. There we can look at, first of all, let's stipulate that the third term in the first row, that's VUB, the coupling of the first and third generation quarks, is negligible when squared. And so all of the action is between VUS and VUD. And they can be evaluated several ways. So from beta decay, most traditionally it's been super loud Fermi beta decay 0+ to 0+ nuclear transitions, which are directly sensitive to VUD, unlike neutron beta decay, which has the Gamow-Teller component, the axial vector GA, so we have to take that account. Not so in the nuclear case. And you get a direct VUD measurement. Then in the kaon system, you can look at several decays, K mu2, comparing that to pi mu2 or KE3 by itself, and you can get a measure of VUS. Of course, all these three should intersect in one point, which is consistent with unitarity, which would be the circle of VUS squared plus VUD squared equal 1. When we look at the actual state of affairs, there's some discrepancy. This is now this vicinity of this point blown up extremely by an extremely large factor. We see that the super loud nuclear beta decays and the neutron beta decay results, which for this plot were a selection, as I will say in a moment. They agree as to the unitarity, but there's some room in the kaon sector. And if we dig into the neutron part per se, we're back to our intersection of the ellipse and the straight line that give us the solution. There, the situation is far less satisfactory. We see, as Leah and others have pointed out, there's a discrepancy between the bottle lifetime and the neutron beam decay lifetime on the one hand. So they have different dependencies in the plane of VUD versus lambda. The lambda itself, as determined from beta asymmetries, so that's simply the asymmetry of the decay of the electron momentum versus this polarization vector of the neutron spin, those give a solution like this. And of course, if we look at the electron-neutrino correlations, they're not as precise, but there's a variety of intersections. Super loud Fermi decays give this line. If we look at the CKM unitarity from the kaon sector, then we get this band. So clearly, one has to understand this better on several levels. Between the questions of what is the, is there a real difference between the bottle and beam methods for neutron lifetime? And also, are in fact the beta asymmetry and the electron-neutrino correlations different in their evaluation of lambda? So we propose to actually address both of those. Now you might say, given this situation here, how could I have in the previous slide made the statement that the neutron and the super-large Fermi case agree very well? That's obtained by actually throwing out the particle data group throws out the beam beam measurements of the neutron lifetime. So here's just fresh off the press, released very recently, the ideogram for lambda by the PDG. And what you see is that per KO3, which is all of these are actually beta asymmetry results. So the lambda values are extracted from beta asymmetries, capital A. There are two recent competitive measurements from Aspect here at Acorn. This has received a slight correction in 23, which you wouldn't be able to see the difference on the spot. What we're proposing is a measurement of lambda with this uncertainty from NAB based on the electron-neutrino correlation, and the follow-up PNAB further squishes down the uncertainty. What you can see is that there's been a drift of lambda values over time. It certainly is to this date dominated by beta asymmetry results, and we plan to address that and put the electron-neutrino correlation on an equal footing. There's a certain degree of inconsistency in the latest. Really, it's Aspect that differs from the bulk of all the other effects, all of the other results. And let me point out that the sensitivity of delta lambda to lambda is only slightly worse for the electron-neutrino correlation, about 10% less sensitive than in the electron beta asymmetry. So we plan combined NAB and PNAB to exceed the precision of PKO3 result, which is currently the best. So how do we plan to do that? Let's remind ourselves these are our goals, and we're going to detect electrons directly in silicon detectors, which were designed specifically for our experiment. We're going to measure the electron energy in these silicon detectors. We're going to detect protons after acceleration in the very same silicon detectors and determine the proton's momentum from time of flight over a long flight path where electron detection provides the start pulse. So to accomplish these goals, we had to design and build a complex magnetoelectrostatic apparatus that guides the particles adiabatically or nearly adiabatically to detectors. And the experiment is located at the fundamental neutron physics beamline or beamline 13 at SNS. So how do we get the electron-neutrino angle when we don't detect the neutrino? If we look at the conservation of momentum in neutron beta decay, and we neglect the proton recoil energy, which can be added back in as a correction after the fact, we rearrange the expression. We see that if we measure the kinetic energy of the proton, the energy of the electron, then we know everything. The one remaining uncertainty, the one remaining variable is cosine of the electron-neutrino angle. So we have to determine the electron and proton energies, or in our case, it's going to be the proton momentum by virtue of measuring the time of flight. So what's the phase space of this decay. So here we have proton momentum squared, or essentially kinetic energy, and the electron energy, and the allowed range of values is contained in this nicely shaped area that we call teardrop. And if we take a slice of a constant electron energy anywhere in this teardrop, and project the kinetic energies, or time of flight, if you like, of the proton, we see that the spectra look like a trapezium, where the slope, in fact, of these trapezia are proportional to the parameter little a, electron-neutrino correlation parameter. So we actually have a number of consistency checks built into the experiment, because each of these slices independently measures, well, they certainly are subject to some of the same systematics, but there's an independent evaluation of little a through the slope. Now, what does this look like? The apparatus here is shown in a cross-section as situated in the fundamental physics beamline. The neutrons come in at this level. Here is this yellow level, and there's about 2 meters below the beam height and 6 meters above the pit. And spoiler alert, we're now in the commissioning phase, and full data taking is expected to initiate with this summer. Here's a cross-section through the apparatus, through this magneto-electrostatic spectrometer, and these are the profiles in blue of the magnetic field, and in red the potential that we use in order to accelerate protons for detection. So the protons that will be detected, there are two identical upper and lower detectors. This is the lower one, here's the upper one, where we detect electrons and protons. So the question is, I'll get to that in a moment, why do we need such complicated fields, in particular magnetic field? Because of course, protons and electrons fly in all directions in neutron decay, and we want to collect them in a hermetic device so that we get every pair that occur in the decay region. So to collect them, we actually use, and in fact, we further want to measure the momentum of the protons, so we have to use adiabatic longitudinalization, which works based on the conservation of angular momentum. If we see that the angular momentum, which must be constant for the particles, relates the sine squared of the theta of the angle between the momentum and the magnetic field direction and the magnitude of the magnetic field. So if we go from a region of high magnetic field where the gyration radius is very tight, and we go to a much broader region, then that actually has the effect of aligning the momentum of the particle closer to the direction of the magnetic field. So as you can see, that's exactly what we do here. This is the neutron decay region, and there's a very sharp increase to 4 Tesla, and then it drops off to virtually nothing, 0.1 Tesla, that longitudinalizes the momentum of the proton, and that allows us to measure the time of flight reliably over a 4 meter, 5 meter flight path. So these detectors that we are relying on are shown here in one of our early depictions when we had a very idyllic relationship to them. They've proven to be more thorny than we expected, but nothing that eventually cannot be overcome. They're 15 centimeters in diameter. They're silicon. Their full thickness is 2 millimeters, or 1.5 if we, there would be a slight compromise on the very endpoint detection of the beta spectrum. They do have a dead layer about 100 nanometers, which creates an issue, and they're shown here. This was a joint development between Los Alamos group and the Micron Corporation. These are some of the early calibrations, which shows how well they work. The segmentation is made into 127 pixels, so that no vertex connects more than, every vertex connects only 3 pixels and not 4. So the apparatus will be run in 2 configurations. The main configuration is the NAB-A, where we detect protons only in the upper detector, and that field pinch, that filter that selects a narrow cone of momenta that will then further be longitudinalized in the long flight path for the time of flight. That means that we only see about 1/8 or 1/7 of the produced protons. The others are swept away, they're turned back. But the electrons are detected in both detectors, and the upper detector is at minus 30 kilovolts, and the lower detector is about either ground or -1 kilovolt. The other configuration, which is the NAB-B, which is focusing on the measurement of the Fierz interference term, where we really want to get a very good fix on the spectrum, beta spectrum, reverses, and in fact detects all of the protons below. We don't care about their times of flight. We just want to know that there was a proton. So this is a coincidence measurement in all of its components. And that's also going to be the main configuration for PNAB running. So what are the main sources of uncertainties? There are very many, and some of them are rather gnarly to track down. Among them, so relative field magnitude, so we really need to know the field mapping very accurately, the geometry of the electric and magnetic field distributions as well, electric field inhomogeneities. So we had to be very careful about the composition of our walls and electrode surfaces, because variations of work functions at the level of 10 millivolts were already of concern. The particle interaction physics, backscattering, Bremsstrahlung, proton detection efficiency. So all of these are folded into the detector response functions. If we look at we have to make regular systematics motivated measurements during main data acquisition, which adds somewhat to the overall running time. This is a quantified table of our main systematic uncertainties, and I've highlighted the ones that are really big compared to the rest of them. And we have had a great deal of time to work on them because of the delays in the delivery of the spectrometer, and then the downtimes that happened for various reasons since it was delivered. And we're ready for a reassessment and really careful reevaluation of all of these terms. But as you can see, we do get down to about 10 to the -3, which is our target level. So I mentioned that we're in commissioning, and that started in the summer of 2023, after we had finally resolved a nasty problem with the spectrometer not cooling down. And we did a bunch of different types of runs. Among them also, about 20% of that was normal data taking. And there were a number of electronics and detector issues. The electronics issues had to do with instabilities. So when we looked at all when we connected all the pixels, the electronics just went wild, and we had to disconnect some. So these were some sacrificial detectors, as you can see, pixels over there. So the lower detector was under depleted, and there's also the issue of the calibration of the proton response, the energy there. So with those large caveats, so this was by no means a full-blown, smooth sailing measurement. Nevertheless, we could get at some physics, and here it is. So this was, let me remind the audience, the first measurement of neutron beta decay, electron-proton coincidences that cover most of the phase space of the decay. And that is our teardrop simulated and with the effects shown of the thresholds on electron detection and the realistic proton detection as well. And this is what we actually saw. And it's in excellent agreement. And the most gratifying, and this is without a great deal of cutting, the backgrounds are really quite manageable, and we have in our hand the proof of principle that this method works. There are still challenges to understand the shifts in the proton response. We didn't see it around 20 keV as expected, but closer to 10. That leads to questions about an unknown accumulation of dirt on the surface, which would result in that. So, as I say, I don't want to paint a too rosy a picture, but the experiment in principle works. We're addressing the electronics uncertainties as we speak, although this is coming in relatively slowly. I want to say one thing, though, that the electronics problems, all of these experts we've consulted, and we have a team working on, professionals working, helping us with that at Oak Ridge, they all agreed that these are tractable problems. And that, so our new design boards are either in hand or on their way. One particular set is slightly delayed. So where does this put us? We see that CK immunitarity is currently violated by somewhere between 2 and 3 sigma roughly, and that puts nuclear kaon and neutron decays under scrutiny. I didn't mention that although those super loud Fermi decays look brilliant and wonderful, they actually, there's been constant criticism that the effects of nuclear structure have been underestimated in those analyses over the years, and we really need to have an independent measurement of VUD that can confirm their validity. So with improved accuracy, neutron decay can dominate VUD determination. So there's a range of experiments and techniques that are needed in order to bring this about. All of the relevant goals are actually within, for accuracy, for uncertainties, are within the grasp of NAB and PNAB for lambda, and there are other experiments, particularly beamline decay3, BL3 at NIST. So if we look at the plane here of lambda relative uncertainty and uncertainty in the neutron lifetime, we see, well, the particle data group current limits on those are here. They're inflated by factors of 2 and more. Our goal is with NAB is to get it at this level in lambda with NAB and then PNAB down to here. The per KO3 we will already exceed with NAB, and the only other method that's comparable in precision to the projected goals of PNAB is PERC, which is still in preparation. So we'll have actually a couple of different techniques to get to the interesting range of VUD, and we see that we need this to get down from the current VUD. Well, there's also the lifetime, forthcoming lifetime measurements. So we need to get into this range between the lifetime and the lambda measurements. And prospects are good. Now, here are the collaborating institutions. And I want to point out one here, which is UNAM, where we are currently situated. The major sources of funding have come from these institutions. And I cannot overemphasize how warmly we invite further collaboration from Latin American groups, including Mexico, of course, and all others, to join this difficult and challenging experiments. And I do not want to paint too rosy a picture because there are very significant challenges to understanding the systematics truly at the level where we aim. Thank you.
Thanks, Dinko. So we have time for questions. Is there any?
So at the end, you mentioned some uncertainties in the nuclear structure calculations of the super allowed beta decays. How about hadronic uncertainties in decay on decay?
So I'm not the expert to speak on that, but there are two, if we go back, let me try it, the wrong button again. So there are two ways of addressing this. Here we go. There's K3 alone or the ratio K mu2 by pi mu2. So to my understanding, the combination of these actually addresses some of the systematics, but I'm not the expert to speak on that. Bill Marciano has told me that that combination together with a remeasurement of the pi and beta decay, which is the least afflicted by any kinds of hadronic corrections. And in fact, it was my group that did the current pi and beta decay experiment. That would beat certainly all these other approaches in terms of theoretical cleanliness if it were not for the 10 to the minus 8 branching ratio, which makes it infinitely difficult to get at counting statistics in a lifetime. But people who know much more than I have been looking at this very carefully, and the claim is that that'll be sorted. But they need to really make sure that all of this is that the components entering these ratios and calculations are right. And that's why Bill is actually pressing for a renewed pi and beta decay experiment by improving the limits by a factor of 3. So then they could actually look at the consistency with KE3. So pi E3 is the one we measure. And that's too big on the VUD. So the uncertainties here would be too wide. But if we can get them down by a factor of 3, that already in combination with the KM results gets us to a point where it's significant as a consistency check. Yes.
So thank you. I mean, I am from the field of double beta decay, and our central problem now is the GA effective value, which is very much different from the one in the single beta decay in the neutron decay. I mean, is there any chance to perform a kind of systematics on single beta decay for, say, heavy nuclei to determine precisely that value? Because for on the double beta decay of germanium or double beta decay of neodymium, also the GA effective can vary from 1.2 up to 1.1 or even small values.
So I'm not the person to answer that question with certainty and expertise. What I do know is that in addition to the 0+ to 0+ super-large Fermi decays, there's a push to do mirror decays, which are precisely what you're saying. And with some luck, there will be a consistency check of that in the coming years. I have not followed closely where that effort stands today, but it's a very good question. It's an interesting point, really. Yes.
There is one, and then.
So we propose, in fact, to look for to determine the VUD from mirror transitions in nuclei. The problem is there that you do not determine the ratio between the axial vector and the vector that you need, like naked one, but you determine the ratio of the axial vector to vector multiplied by the Gamow-Taylor matrix element divided by the Fermi matrix element. So what these systematics from mirror transition, we determine, in fact, from another observable, that mixing ratio, and then inject that into the lifetime in order to extract VUD. But we don't have, I mean, every transition has a different value of that. We call this mixing ratio because it contains also the matrix elements.
Yeah, that was the matrix elements were the bone of contention in the super-loud Fermi decays because there were theorists criticizing the method by which the isospin breaking was actually evaluated in these, but I'm not an expert.
So, Libertad, can I make a comment? So I'm not an expert either, but on the Monday's session, Jason Holt made a comment that the GA effective has been solved if you're very consistent with the Carrel effective field theory. But if he's not here, that's all I can say.
Okay. Okay. If there are no more questions, let's thank the speaker. Then I have an announcement for all of those that sign up for the